How's everyone doing today? It does not feel like Friday after having yesterday off. I feel scammed. Doing good. All right, let me gonna grab some water real quick. I'll be right back. All right. Okay, so yesterday we started looking at double integrals, and we looked at them over. So so for double integrals, we're integrating a function of x and y over some region in the xy plane. Yesterday, we looked at how to integrate over the simplest possible regions in the xy plane, just rectangles, where, say, x goes from A to B, and y goes from C to D. And we saw the way that we integrate these. So we evaluate the double integral over such a rectangle R. So if R is the rectangle, x goes from A to B, y goes from C to D. So if we evaluate the double integral of a function f of x, y over the rectangular region R with respect to area, the way we do that is we just turn that into an iterated integral. First, we integrate with respect to x, and then with respect to y. So we integrate x, goes from A to B. So that's our first integral. We treat y as a constant, integrate as usual with respect to x, for x goes from A to B. And then we've integrated out x, and we're just left with a function of y. And we integrate that function from y equals C to D. So we can do that. Or Fubini's theorem says we could also integrate with respect to y first, and we get the same thing. So those are two ways we can evaluate this integral. So we integrate with respect to y first. Y goes from C to D. Treat x as a constant, integrate with respect to y from C to D. Y is going to disappear at the end. We're just left with a function of x, and we integrate that from A to B. And that's how we integrate over rectangles. So in 140 and 141, we were just integrating functions of one variable over intervals. And so the only thing that made an integral complicated for functions of one variable was the function you're integrating itself. But for functions of two variables now, you're integrating over a region in the plane. And you could have a simple function to integrate, but a complicated integral to evaluate, because now Now you can evaluate over complicated regions. You can integrate over complicated regions in the plane now. So life is very easy when you're integrating over rectangles. But unfortunately, in real life, we would like to integrate over more than just rectangles. And today we're going to look at somewhat more general regions and how we integrate over those. So we're going to look at double integrals over general regions, not truly general regions, but more general regions than a rectangle. Okay, so I'm not gonna go through the derivation of all this, but the way we can think of integrating over these rectangles, let's do it this way. Is the following way. So notice this rectangular region D, or we'll call it, yeah, whatever, we'll call it D, because we're going to call all the regions D. Now, it's bounded on the left by, or let's start the other way. It's bounded on the bottom by the curve y equals c, and bounded above by the curve y equals d. So if we draw a vertical line anywhere that intersects this region D, so any vertical line you intersect with the region D, it's going to hit the bottom of the region D in the curve y equals c. So the bottom, no matter where, is going to be the same curve y equals c, and the top is going to be the same curve y equals d. And so y is bounded by the functions y equals c and y equals d. Those are just numbers, but as we'll see in a sec, we can replace those with functions of x, more complicated curves, and do the same thing. And then x is just bounded between numbers a and b. Okay, so we can do more complicated things now. Instead of having y just between y equals a constant and y equals a constant, we could have, say, we could have, say, okay, so this region now is bounded below by a curve y equals g1 of x, and above by y equals g2 of x. And to the left and the right, we just say x is bounded by numbers. But the important thing is, if you do the same thing we did over here, if you draw a vertical line anywhere, whoops, intersecting the region D, every time it hits D, it's going to hit the bottom in the same curve, y equals g1 of x. And on the top, it's going to hit the same curve, y equals g2 of x. And so here we'd say the region D, oh my God, stop it. We'd say for D, y is bounded below by the function g1 of x, and above by g2 of x. And then we'd say x is just bounded by the numbers a and b. So we say this is a vertically simple region. So a vertically simple region is going to have if you do the vertical line test, it's going to have a uniform bottom curve and a uniform top curve. Any vertical line is going to hit the same bottom curve. You can use the same equation for the bottom curve. And same thing, it's going to hit the top. Each vertical line is going to hit the same top curve on top. The important thing is that the bottom curve you can write as the same equation y equals g1 of x, and the top, the same equation y equals g2 of x. And then we just say x goes from a to b. So that's one type of region we're going to look at today. The other type is the opposite now. Instead of a definite top and bottom curve, we have a definite left and right curve. So suppose we have this region D. So if we do the vertical line test here, it's going to fail, because if we do, say, a vertical line here, oops, whatever this guy is our bottom curve. And this guy here is our top curve. But if we do it over here, now this piece is our top curve, and this guy is our bottom curve. So the top curve is going to be different depending on where you do your vertical line. So we can't say y is bounded below by y equals something, some curve, and above by some curve, because depending on where you are, there's a different top curve. But what we can say is that there's definitely a left curve and a right curve. So a left boundary and a right boundary for this. And you do the same thing. You do the horizontal line test. So we'll say this left guy is x equals h1 of y. So x is now a function of y, the left curve. So x is the left-right variable. And so we're bounded to the left by x equals some function of y, and to the right by x equals some other function of y. And so similarly, you do like a horizontal line test. You're always going to hit the left boundary on h1 of y and the right boundary on x equals h2 of y. And then we say y goes from C to D. So this region D would be x is bounded below, where x is smaller, to the left, by the left curve h1 of y, and above by the function h2 of y. And then y is bounded between the numbers c and d. And we say this is horizontally simple. So we say our region D has definite left and definite right curves. Right, you do your horizontal line test. It's always going to hit your region D on the left side in the same curve, and on the right side in the same curve on that side. Okay, so does this make sense so far? Any questions about these two types of regions? So we have the vertically simple region, where our region has a definite top and bottom curve. Those are going to be y is equal to some function of x, and then we just say x goes from some number to some number. And then the other type of region is where there's a definite left curve and a definite right curve. So the left is x is a function of y, the right is x is some other function of y, and then y goes from some number to some number. Okay, so the way we're going to integrate these is the same way. We're going to do an iterated integral, except in this case, the order we integrate depends on whether we're vertically simple or horizontally simple. Let me do it this way. So suppose we have a vertically simple region D. Sure. Okay. So you do your vertical line test. You're always hitting the top and the same curve, and the bottom and the same curve. So the bottom is y equals, we'll say, g1 of x, some function of x, and the top is y equals g2 of x. And then x is going to go, whoops, no, let's say from A to B. So vertically simple, we got a top curve and a bottom curve. And so when we're vertically simple, the vertical variable is going to be bounded by functions of x, of the other one. So the vertical variable y is going to be bounded by functions of the other variable. So below, we have g1 of x, and above we have g2 of x. And then the other guys, we're just going to say x is bounded by a and b. X goes from A to B. Okay. So when we integrate it over a rectangle, we could integrate with respect to x first or with respect to y first, and we get the same answer. And we said, x goes from A to B, y goes from C to D. So we're going to do the same thing here, except now, here's the thing. When you integrate, when you do a definite integral, you always want to get a number at the end. And so here, for one of our variables, y, the bounds are going to be functions and not numbers. So when you integrate with respect to y, you do your antiderivative, and then you're going to plug in functions of x in where you see y. If you're doing that last, you're going to end up with something involving x at the end, which doesn't make sense, right? So since y is bounded by functions, you have to integrate with respect to y first. So y goes from g1 of x up to g2 of x. Sorry, let me say, okay, so we're integrating some function of x and y over our region D, our vertically simple region D. With respect to area, the way we do that is first we integrate with respect to the variable bounded by functions, which in this case is y. And then we integrate with respect to the variable bounded by numbers, which is our x. So at the end, we're plugging in numbers and we're going to get a number. So we're going to want to integrate in whatever order will give us plugging in numbers last. So the last integral we want to perform is with respect to the variable bounded by numbers. Does that make sense? And then if x is if d is horizontally simple, right? If x is bounded by functions of y now, that's now the variable bounded by functions. And so we need to, and if y is bounded, goes from c to d, we integrate with respect to y last, because we need to plug in numbers last. Okay, so let's do some examples. That's always the easiest way to clear up, get the hang of this stuff. Okay. So let's evaluate the integral over the region D of x squared y with respect to area. And here D is going to be the region in the following picture. So it's bounded by, oops, hang on. So this is our region D. So on top, well, you know what? I already gave it away here, but is this vertically simple, horizontally simple, both, neither? Vertically simple, if I do a vertical line test, am I always going to hit the same top curve and the same bottom curve? So no matter where I intersect a vertical line, I'm always going to hit the top on this guy here. Well, let me go ahead and write down what those are. So this top guy is y equals square root of x, and this bottom guy is y equals 1 over x. So no matter where you intersect a vertical line, you're always going to hit the top on y equals root x and the bottom on y equals 1 over x. It's not horizontally simple, though, because doing the same thing here, now y equals root x is the left curve, and x equals 3 is the right curve. But down here, now y equals 1 over x is the left curve, and x equals 3 is the right curve. So it fails the horizontal line test. So it's not horizontally simple. We'll see you can be both horizontally and vertically simple, but in this case, so it's vertically simple. So the vertical variable y is going to be bounded by functions of x. So y is bounded below by 1 over x and above by square root x. And then x goes from 1 to 3. Okay. Does everyone understand how we got to this point? Okay. So now, since y is bounded by functions, we're integrating with respect to y first. So we integrate x squared y. First, with respect to y is bounded below by 1 over x and above by square root x. And then we're integrating with respect to x. X goes from 1 to 3. So let's do the inner integral first. We're integrating x squared y with respect to y. So we're integrating with respect to y, we're treating everything but y as a constant. So x squared is now a constant. What happens to x squared y when we integrate with respect to y? What does that become?
One half x squared y squared.
Right. So x squared is just a constant that hangs around. Y becomes 1/2 y squared. So we get 1/2 x squared y squared. Is x equal 3 part of the graph? Yeah. So x equals 3 is sort of the right boundary of this guy, Nick. Yeah. And we're evaluating that from y equals 1 over x up to y equals square root x. So we have the 1/2 x squared. We're treating it as a constant. And then y squared plugging in root x, we get root x squared, which is x, minus 1 over x quantity squared, which is 1 over x squared. And we can multiply through and simplify this. So we get 1/2 x cubed minus 1/2 x squared times 1 over x squared, which is just 1/2. So that's our inner integral. Now we just have a function of x, and we integrate that from x equals 1 to 3. So 1/2 x cubed minus 1/2. Give myself some room. So 1/2 x cubed becomes 1/8 x to the 4. And minus 1/2 becomes minus 1/2 x. And we're evaluating that from x equals 1 up to x equals 3. So we get 1/8. So 3 cubed is going to be 27. All right, so we have 27 over 8 minus 1/2 x valued at 3, so 3 over 2, minus quantity. So 1 over 8 times 1 to the 4, so 1/8, minus 1/2. And so we get 27 over 8 minus 1/8. Should get a round number, right?
Professor, isn't it 3 to the 4, not x cubed on that?
On which?
You did 27 over 8, but wouldn't it be 3 times 3 times 3 times 3?
Oh, 3 to the 4, not 3 to the 3. Yes, sorry. 81. There we go. I was like, yeah, this doesn't make sense. Right. Okay. So we get 81 over 8 minus 1 over 8 is 80 over 8, which is 10. Minus 3 halves minus negative 1/2. So 3/2 plus 1/2 is 2. Sorry, negative 3/2 minus, so minus 1. So we get 9. Right. But the big thing with all these integration problems is knowing how to set it up. Like in an exam, if you make a, for instance, a dumb algebraic mistake like that, that's going to be, minus a point here or whatever. But if you don't know how to set up the integral, then you're hopeless. You're not going to get like almost any points at all. So the important part is noticing that this is a vertically simple region. There's always a top curve and a bottom curve, and then knowing to integrate. So then bounding y between functions of x, knowing to integrate with respect to y first, and then getting the correct bounds, etc. Setting up the integral correctly.
And we integrate with respect to y first because it's vertically simple, right?
Right, because we integrate with respect to y first because y is bounded by functions of x. So the bounds for y are going to be functions, not numbers. And if you plug that in last, then the answer you're going to get is going to involve variables, which the answer has to be a number. It can't involve variables. So you have to integrate with respect to that first. If that makes sense. Okay, let's do another example. So let's find the volume. Below the plane z equals 2x plus 3y, and above the triangle in the xy plane with vertices 0, 0, 2, 2, and 4, 2. Okay, so it's a little difficult to draw a picture of this, but so remember we think of here, let's do it this way. So in the xy plane, we have the triangle with vertices 0, 0, 2, 2. So 2, 2, and 4, 2. So this is our triangle in the xy plane. So we're looking at the volume below some plane and above this region here. We'll call that D. Actually, that's actually kind of a terrible picture, but here, let me show you in the book what it looks like, to give you an idea. It's this region here. So we're trying to find the volume of this solid region. All right, so here's our triangle. They kind of rotate it from where I did. And here's the piece of the plane. So it's a solid region bounded above by that plane, below by that triangle in the XY plane. It's okay. You don't need to be able to draw the three-dimensional region in this case. The important thing is, oops, sorry, the region in the XY plane, the triangular region. Okay, so we're looking for volume below the surface, where that surface is the graph of some function. Let me do it this way. So, Jesus. Here's our plane. So z equals 2x plus 3y. So we know, I mentioned this briefly. No, I didn't mention this briefly, but the volume below the graph of the function f of xy, so below the surface z equals f of xy, and above some region D in the XY plane is going to be the integral over D of that function that the top guy is the graph of. Okay, so the thing we're going to be integrating is this guy. This guy is the graph of the function 2x plus 3y. It's the surface z equals 2x plus 3y. And so that's going to be what we're integrating to find the volume below that. So now we know what we're integrating. Now we need to look at our region D and figure out what the bounds are and what we're going to integrate. With this, what order we're going to integrate it in. So let's look at the region D here. Let's just look in the plane. Okay, so we have the region we're integrating over is a triangle, and it's going to have vertices 0, 0, 2, 2, and 4, 2. Okay. So is this guy going to be vertically simple? It's not vertically simple. Because if you do the vertical line test, depending on what vertical line you intersect D with, the top curve is going to be different, right? For the first one, the top curve is this guy, and the second one, the top curve is this guy, and those are two different curves. One is y equals, we'll figure that out in a second. The other is y equals 2. So it's not vertically simple. How about horizontally simple? If we do the horizontal line test, is it always going to hit the left in the same curve and the right in the same curve? Yes, it is horizontally simple, right? Do a horizontal line somehow. You're always going to hit the left on this curve and the right on this curve. So it's horizontally simple. So that means x is going to be bounded by functions. So we need to write the left curve and the right curve as x equals some function of y. And then y, we're just going to bound by numbers. Okay. So let's figure out what the left and right curves are. We can just write it as y equals something. That'll be easiest. And then let's get x by itself for each of these. So the left curve, we have the piece of the line from 0, 0 to 2, 2. What line is that? Y equals what? Y equals x, right? It's got slope 1. The y-intercept is 0. So y equals x. The right curve, it's the line from 0, 0 to 4, 2. So the y-intercept is 0. What's the slope? So we go up 2 over 4. The slope is going to be what? 1/2, right? So this is y equals 1/2 x, the right curve. So getting x by itself on both of these, we have the left curve is x equals y. That's where x is bounded below by that guy. That's where x is smallest on the left. Sorry, the left curve is x equals y. And getting x by itself on the other one, just multiply both sides by 2. We get x is 2y. So x is bounded below by y and above by 2y. Right? The left curve is x equals y. The right curve is x equals 2y. Does everyone see that? So we saw it's horizontally simple. The horizontal variable x is going to be bounded by functions of the other variable y. And so we just figure out what those curves are, get x by itself, and then that's how we do that. So then y is going to go from what to what? What's the smallest value of y in this triangle? 0. And what's the largest value of y? 2. And so now we have our bounds. So we said we were integrating 2x plus 3y. So it's horizontally simple. X is going to be bounded by functions. So we got to integrate with respect to x first. So x goes from y up to 2y. Our inner integral is going to be with respect to x. And then we integrate with respect to y. Y goes from 0 to 2. So let's evaluate this inner integral. Okay, so 2x plus 3y. We're integrating with respect to x. So we're treating y as a constant, integrating as usual with respect to x. What happens to 2x when we integrate it?
X squared.
Right, we get x squared. And how about 3y? So 3y is a constant. What happens when you integrate that constant with respect to x?
It's just 3yx.
Right. So it's just a constant. So a constant becomes that constant times x. So it's just 3yx. And we're evaluating this from x equals y up to x equals 2y. So we get, evaluating at 2y, so we get 2y quantity squared is 4y squared plus 3y times 2y. And then minus evaluating at y, so we get y squared plus 3y times y. give myself some room here. And so this is, so we have 4y squared plus 6y squared. So that's 10y squared. Minus y squared is 9y squared. Minus 3y squared is 6y squared. So our inner integral is 6y squared. So now we plug that into the outer integral here and integrate from 0 to 2. So 6y squared, when we integrate it with respect to y, becomes 2y cubed. And we evaluate that from y equals 0 to 2. And so we get 2 times, I'll just pull the 2 out. 2 cubed is 8, minus 0 cubed is 0. So we get 16. Okay, so for this problem, we wanted to find the volume of some solid region, right? And that solid region, we're told it's below the graph of some function. So z equals some function of x and y, and above some region D in the xy plane. So that volume is just going to be the integral over that region D in the xy plane of that function where the surface on top is the graph of that function. And then we looked at the region D in the xy plane and figured out it was horizontally simple. So we're integrating with respect to x first, et cetera, et cetera. That's the process for this problem. Any questions about this problem? So we know how to integrate over rectangles. That's easy. X and y both lie between numbers. You can integrate with respect to whichever one you want to first. But horizontally or vertically simple regions, which you integrate with respect to first, depends on whether you're vertically simple or horizontally simple. And you want to integrate with respect to the variable bounded by functions first, in that case. Okay. So we'll pick this up again on Monday. Do some more examples, look at some other stuff in this chapter. But yeah, have a nice weekend, and I'll see y'all on Monday. Have a good one, guys.
So just real quick, before we leave, the difference between horizontally simple and the if it's vertically simple, is we base that off the vertical line test. Is that what you were saying? Like
yeah, so if it passes the vertical line test, it's vertically simple. If it always hits the top in the same curve, if you can always write that top curve as a single y equals some function of x, then you have a uniform top curve. And if it always hits the bottom curve on y equals something. So if it has the same top curve, same bottom curve, no matter what vertical line you intersect it with, it passes the vertical line test, it's vertically simple. Horizontal line test means same left curve and same right curve. So we'll see next time. You can actually be both vertically and horizontally simple.
Okay.
So for instance, of course it would do this. If we had like this triangle here, right? So it's vertically simple because, right, always intersects the top in the sloped guy and the bottom in y equals 0. And it's also horizontally simple because it always hits the left on y equals 0 or x equals 0 and the right on that slope line there.
Okay, sounds good.
And you can also be neither, but yeah.
Okay, thank you.
Have a good one.
Hello.
Yes.
I just wanted to remind you that my exam 1 still hasn't been graded.
Yes, yes. I realized that this morning. I'm grading all the exam 2s. I am